All right, good morning, everyone. My name is Demir Akçur, and I'm a PhD student in civil engineering at Johns Hopkins University. Today, we have our own first mini-symposium, Engineering with Julia. So myself, Christopher Mohn, who is sitting right here, and Cole Miller, I don't know if he is here, bridge engineer from HDR Construction Company, have decided that we need to really promote Julia among engineers, so we have decided to have this mini symposium. And today I'm happy to present our first speaker, Rajeev Voleti, who will be opening first ever Engineering with Julia mini symposium.
Right. I'll just use this. Okay. Does this work? Yeah, oh, cool. Okay, good morning guys. Today I'm going to talk about AerialVehicles.jl and sort of the incremental update that makes it possible to do cooperative payload manipulation, specifically with 2 quadrotors and trying to carry a single payload. I'll start with a bit of a recap on my talk last year. The flat equation quadrotor model is derived using a force balance on a rigid body. The quadrotor is a differentially flat system. For a differentially flat system, all system states and inputs can be expressed in terms of a set of flat outputs and their derivatives. In our case, the flat outputs are the position in space, x, y, z, and the heading, psi. We use position, velocity, rotation matrix, and angular velocity to describe the state of our quadrotor system. The dynamics are defined in MTK, at least initially. The quadrotor is a very well-documented problem in controls and serves as a platform to showcase controls, estimation, and various other applications. To follow sort of trajectories that are designed, we use a nonlinear geometric controller. The idea behind this is similar to backstepping for those a little bit more familiar with control. It involves designing the desired dynamics for the quadrotor and then stepping back to cancel all the non-linearities to make sure that the dynamics follow what is desired as opposed to just throwing a PID on there. The advantages of using the geometric controller are that it accounts for the specific non-linearity of the problem, and the state decays to the desired value exponentially. As is clear from the illustration, it's really hard to achieve that level of stability even with an extremely fine-tuned PID controller. So this allows us to do some fun things, acrobatic maneuvers, like stabilizing for falling quad or having it track like a really tight spiral, much more effectively than a PID would, and it's a lot less cumbersome. This is the overall structure of the trajectory optimization process with the quadrotor using a geometric controller. It was presented at JuliaCon last year. So based on an array of sort of waypoints and corresponding time required for each segment that needs to be designed, the trajectory optimizer synthesizes a desired output, which the geometric controller uses, along with state feedback to synthesize the control to make the quadrotor follow the desired trajectory. The control generation and trajectory optimization has been done using dyad control systems, and the quadrotor model and the geometric controller is part of the AerialVehicles.jl library. So this was my presentation last year. Just a quick recap in that we have an autonomous rendezvous of 2 ground vehicles with varying dynamics. They don't have the same dynamics, and a quadrotor utilizing a polynomial trajectory following geometric controller. So the quadrotor hits 3 waypoints before landing, and it triggers a cooperation between the ground vehicles, at which point they start to receive the time to go of the quadrotor every second, and they just autonomously achieve rendezvous. There's no manual control. It all happens by itself. So building upon sort of a theme of cooperation, the heart of the demonstration today is being able to define multi-body models. So the whole system is sort of comprised of 4 rotor components a rigid frame, a cable with n links, 3 for this demonstration, and a payload that all lay inside the world frame. They're all easy to understand and define independently as components. And to assemble the cooperative system, you just have to connect the frame of one component to the other. And as is evident from the simulation results on the right, it makes thinking about the control problem much easier. So in this case, I've leveraged the payload position and the orientation within the framework of the geometric controller, taking into account the physics that is sort of required and what the quad needs to do to stabilize it. And yeah, the geometric controller used is an incremental update. It's not exactly the same as what it was, but it gets the job done. Yeah, so we have a demonstration of 2 multi-body quadrotors that are attached to a single payload. It looks quite mundane when it operates as it should, considering the trajectories are snap optimized, which means they're extremely smooth. So they're quite boring to look at. So in this simulation, I've intentionally initialized the system adversely with a slightly heavier than usual payload to study the stabilization process. The payload is tasked to track a figure of 8. Even when the payload is initialized near horizontally to the cooperative system, the quadrotors manage to stabilize the system. And both these quadrotors use the modified geometric controller. And state estimation is not a thing yet, which I'll talk about a little later. But yeah, this is the theme of this year's cooperation. Takeaways. Aerial vehicles can be used to perform a variety of tasks. A component-based multi-body model has been shown to be effective and intuitive. Cooperative payload manipulation leveraging the multi-body modeling framework has been achieved. For future work, multi-body modeling is highly experimental and unreleased, and it will be released into the dyad ecosystem of tools when it is. Next, I would also want to explore complex geometric payload manipulation and have corridor constraints, which makes things a lot harder than just being like the world's your oyster. State estimation, because it's hard to estimate where the payload is and what the orientation is. There's no sensors that do that instantaneously. And so building up a state estimation problem to find those states would be exciting. Some of the other stuff that I have going on is AerialVehicles.jl has wind models. You can plug in wind into the system and see how it does in something a little bit more realistic and not like a closed room. And finally, deeper integration with dyad for running analysis on some of these multi-body systems or cooperative systems and optimizing performance. Yep, that's all I have. Thanks.
All right, thank you. We have time for one question. All right, I do have one question.
Yes.
When you try to move the load with 2 quadrocopters, right? Mm-hmm. Do you have any geometric constraints to prevent the collision between them in the models that you have created?
There is a way to do that. I do that manually currently. Okay. So I synthesize very smooth trajectories for the quadrotors to follow and enforce a manual offset, which sort of makes it so they don't collide, which is very ideal. I know, but usually some of these collision avoidance mechanisms are sort of an inner loop, which is when they sort of get close to each other, there is a control input that sort of triggers that moves them away. You can do that with artificial potential fields. There's a lot of ways of doing it, but that's not the theme of this presentation. I can add that in the loop.